Hello all my dear students, grade 12 physics advanced stream. Unit number 5, current and resistance. Lesson number 5.3, resistance and resistivity. Learning objectives. Measure the thermal and electrical resistivity and conductivity of various materials and explain the results. Use Ohm's law and electrical resistance in solving circuit problems. Develop a tool, sketch, graphs, or qualitative description to compare between resistivity and conductivity. To calculate resistance of resistor by reading the color code. To use the temperature coefficient of resistivity to solve problems involving changing temperature. Keywords. Resistance R, resistivity ρ, conductance G, conductivity sigma, and Ohm's law. Some materials conduct electricity better than others. Applying a given potential difference across a good conductor results in a relatively large current, but applying the same potential difference across an insulator produces little current. Resistivity ρ. What is it? Resistivity is the opposite of conductivity. It is a measure of how effectively a material slows down the flow of electric current. Insulators have a high resistivity rating. Materials such as metals and other conductors have a low resistivity rating. The resistance R is the opposite of conductance G. It's a material's opposition to the flow of electric current. If a non-electric potential difference, delta V, is applied across a conductor and the resulting current I is measured, the resistance of the conductor is given by R equal delta V divided by electric current I. A conductor resistance is defined as the ratio of applied voltage delta V to the current produced I. The resistance R is a scalar quantity with only magnitude without direction. The measurement unit of resistance is the volt per ampere, which has been given the name ohm, and symbol ohm, it is the capital Greek letter omega. So 1 ohm equal 1 volt per 1 ampere. It is named in honor of the German physicist Georg Simon Ohm. Rearrangement of equation R equal delta V divided by electric current I results in I equal delta V divided by R. This equation is commonly referred to as Ohm's law. Macroscopic versus microscopic. Current I driven by potential difference. Current density J driven by electric field E. Experiences resistance R. Experiences resistivity ρ. In macroscopic Ohm's law, I equal V over R. But in microscopic Ohm's law, J equal E over ρ. Current can be measured using an ammeter. Two electrical measuring devices, X and Y, are placed in the circuit as shown to measure properties of the resistor. Which of the following descriptions is correct? X measures current and Y measures voltage. X measures voltage and Y measures current. X and Y measure current, or X and Y measure voltage. Yes, the answer is X measures current and Y measures voltage. Current is measured at a location, ammeters in series. Voltage, potential difference between two locations, voltmeters in parallel. Example 2. How does the current entering the resistor I1 compare to the current leaving the resistor I2. I1 less than I2, I1 greater than I2, or I1 equal I2. The right answer is I1 equal I2. That's because charge conservation. Charge cannot be created or destroyed. Energy is dissipated as current flows through a resistance, but charge is conserved, so current in equal current out. Example 3. You double the voltage across a certain conductor and you observe the current increases 3 times. What can you conclude? Ohm's law is obeyed since the current still increases. When V increases, Ohm's law is not obeyed. This has nothing to do with Ohm's law. The right answer is Ohm's law is not obeyed. Ohm's law, I equal delta V over R, states that the relationship between voltage and current is linear. Thus, for conductor that obeys Ohm's law, the current must double when you double the voltage. Resistance can be calculated for any object. Good conductor, that means low resistance, and poor conductor, that means high resistance. All circuit elements have some resistance. The resistance of connecting wire leads is considered negligible. Sometimes devices are described in terms of conductance G, defined as G equal I divided by delta V equal inverse R. Conductance has the SI derived unit of Siemens, S capital, and 1 Siemens equal ampere per volt equal ohm power minus 1. In some conductors, the resistivity depends on the direction in which the current is flowing. Here we assume that the resistivity of the material is uniform for all directions of the current. The resistance of a device depends on the material of which the device is made, as well as its geometry. As stated earlier, the resistivity of material characterizes how much it opposes the flow of current. The resistivity is defined in terms of the magnitude of the applied electric field E and the magnitude of the resulting current density J. Rho equal E over J. The current density J flowing from a given electric field E depends on the resistivity Rho of the material, or its inverse conductivity, sigma equal 1 over rho. Then J equal E over rho equal sigma times E. And high resistivity rho means low current density. Exercise number 4. A 1.8 millimeter diameter copper wire carries 15 ampere to a household appliance. What is the electric field in the wire? The resistivity of the copper is 1.68 times 10 power minus 8 ohm times meter. Ohm's law states that J equal E over rho. Resistivity of copper, rho equal 1.68 times 10 power minus 8 ohm meter. Then current density J equal I over A equal I over pi R square equal 15 over pi times 0.9 times 10 power minus 3 square equal 5.9 times 10 power 6 ampere per meter square. And the electric field E equal J times rho equal 5.9 times 10 power 6 times 1.68 times 10 power minus 8 equal 0.099 volt per meter. Table 5.1 lists the resistivities of some representative conductors at 20 degrees Celsius. As you can see, typical values for the resistivity of metal conductors used in wires are on the order of 10 power minus 8 ohm meter. Several metals alloys listed in table 5.1 have useful properties. For example, copper has a resistivity of about 2 times 10 power minus 8 ohm meter. But wire made from nickel chrome, 80% nickel and 20% chromium, is often used as a heating element in devices such as toasters. The resistivity of nickel chrome 108 times 10 power minus 8 ohms meter is about 50 times that of copper. Thus, when current is run through the nickel chrome wires of the toaster, the wires dissipated power and heat up until it glows with a dull red color, while the copper wires of the electrical cord that connects the toaster to the wall remain cold. The resistance of a conductor can be found from its resistivity and its geometry. R equal rho times L divided by A. Rho is the resistivity of the conductor measured by ohm meter, where L is the length of the wire and A is the cross-sectional area. From this equation, the unit of resistance equal ohm meter for resistivity times meter for length over meter square for cross-sectional area. Result is ohm. Increase the length, flow of electrons embedded, but increase the cross-sectional area, flow enhanced. The length of the conductor is similar to the length of the hallway. A shorter hallway would allow people to move through at a higher rate than a longer one. So, shorter conductor would allow electrons to move through at a higher rate than a longer one too. It can be shown that R is directly proportional with L, and also the resistance inversely proportional to cross-sectional area. Increasing the cross-sectional area increases the number of available electrons. That means decreasing resistance. Exercise number 5. A copper wire 0.5 centimeter in diameter and 70 centimeter long connected your car's battery to the starter motor. What is the wire's resistance? Recall that the resistivity of copper is 1.68 times 10 power minus 8 ohms meter. A equal pi r square and R equal 5 times 10 to power minus 3 divided by 2. It's equal 2.5 times 10 to power minus 3 meters. R equal rho times L divided by A equal 1.68 times 10 power minus 8 times 0.7 divided by pi times 2.5 times 10 power minus 3 square equal 6.0 times 10 power minus 4 ohms. If the starter motor draw a current of 170 ampere, what is the potential difference across the wire? Ohm's law states that delta V equal I times R equal 170 times 6 times 10 power minus 4 equal 0.1 volt. 3 conducting wires made of the same material as in the figure. Firstly, find the resistance of wire X and the resistance of wire Y. Second, find the resistivity of the material. Rx equal 10 ohms because the cross-sectional area is half the cross-sectional area for the first one. Ry equal 20 because it's tall twice the tall for the second wire. To determine the resistivity, we can use the equation rho equal R times A divided by L equal 5 times 2 times 10 power minus 6 divided by 4 equal 2.5 times 10 power minus 6 ohms meter. Sometimes materials are satisfied in terms of their conductivity sigma rather than their resistivity rho, which is defined as sigma equal 1 over rho equal L divided by R times A. And the measurement unit of conductivity are ohm meter power minus 1. Exercise number 7. A wire 10 meter long consists of 5 meter of copper followed by 5 meter of aluminum of equal diameter of 1 millimeter. A voltage of 80 volts is placed across the composite wire. Firstly, what is the total resistance of the wire? Second, what is the current flow through the wire? From the table 5.1, resistivity for copper equal 1.72 times 10 power minus 8 ohm meter. And resistivity for aluminum equal 2.82 times 10 power minus 8 ohm meter. Cross-sectional area for copper equal cross-sectional area for aluminum equal pi r square equal 7.85 times 10 power minus 7 meter square. R total equal R for copper plus R for aluminum equal rho for copper plus rho for aluminum times L divided by cross-sectional area A. Then R total equal 1.72 plus 2.82 times 10 power minus 8 times 5 divided by 7.85 times 10 power minus 7. Then R total equal 0.29 ohms. I equal delta V over R equal 80 divided by 0.29. Then I equal 277 amperes. Let's summarize. Thank you all and have a nice time.